something moves among the stars, and it is neither a planet nor a comet that we could recognize. This object is now called 3 Ibara Atlas and rewrites our conceptions of bodies from the far corners of the universe. When astronomers first noticed it in 2023, they called it a comet. However, soon data showed that this visitor behaved strangely, igniting when it was 4 times farther from the Sun than Earth. If you are interested in such documented space science, support our work. Also, let us know which city you are listening from. This script is based on factual data. We draw information from sources at NASA's Jet Propulsion Laboratory and the Center for Near-Earth Object Studies. Now let's return to the story. 3 Ibara Atlas, not from our neighborhood, not from the familiar family of stones and icy spheres of our solar system. Numbers tell a story. When most comets begin their display, developing a classic tail and shining, they are about 2 astronomical units from the Sun. This is twice the distance from Earth, which is predictable and manageable. 3 Ibara Atlas began to glow at a distance of 16 astronomical units, which is 16 times the distance from Earth to our star. This is beyond Saturn, where everything should be cold and dead. The Subaru telescope first captured it on January 13, 2023. It was a moving point that should not have been moving like that. Robert Wyrick from the University of Hawaii confirmed the initial discovery 3 days later using the Canada-France-Hawaii telescope. Subsequent observations from Mauna Kea confirmed the computer calculations. The object followed a hyperbolic trajectory. What does this mean? He is not connected to our sun. He came from another place, passed through our system once, and will never return. But this is where the most interesting part begins. Ordinary interstellar visitors, and we have confirmed only 4 such cases before, are stones, dense asteroids, dark, likely metallic or rocky, that have been ejected from their home systems. Oumuamua in 2017 was about 400 meters long, rotating every 7 hours, reflecting light like polished metal. Ibara Borisov in 2019 was different, icy, but behaved like comets from our system. 3 Ibara Atlas completely disrupt this pattern. It consists of ice, a lot of ice. Spectrographic data shows the presence of water vapor, carbon monoxide, carbon dioxide, classic cometary material, except that comets should not survive interstellar travel. Think about it. The space between solar systems is not empty. It is filled with cosmic radiation that destroys organic molecules and sublimates ice over millions of years. An object made of ice traveling through space for hundreds of thousands or millions of years would appear as a dry shell. However, 3 Ibara Atlas arrived intact. The object was again detected in March 2023 through sky probing in Catania. This time it showed clear signs of desublimation. By April, telescopes from 3 continents were already tracking it. A very large telescope of the European Southern Observatory in Chile recorded spectra showing active sublimation at a distance of 18 astronomical units from the Sun, nearly 3 billion kilometers. At such a distance, the Sun's heat provides about 250 times less energy than the Earth receives. Ordinary physics states that this should not be the case. Sublimating water in space requires a temperature of around 150 kelvins. At 18 astronomical units, the 3 Ibara Atlas should be at a temperature of around 40 kelvins, frozen and dead. Instead, it emits 10 kilograms of water vapor every second, along with carbon monoxide, ammonia, and traces of organic compounds. Activity began early and remained stable. Most comets follow a predictable trajectory. They heat up as they approach the Sun, reach maximum brightness near perihelion, and then fade away as they move away. Halley's Comet shines brightly 10,000 times between aphelion and perihelion. The Hale-Bopp Comet, for example, followed the same scenario in 1997, becoming visible to the naked eye only when it approached 4 astronomical units from the Sun. 3 Ibara Atlas maintained brightness and gas production over a much wider range of distances, reaching 20 astronomical units. It produced about 10 kilograms of water vapor per second. At a distance of 15 astronomical units, it continued to emit the same 10 kilograms per second. At a distance of 10 astronomical units, the rate finally began to increase to 15 kilograms per second. This flat production curve indicates something unusual in its internal structure or composition. If you are interested in documented space science, support us. Also, let us know which city you are listening from. This scenario is based on facts and research using sources from the European Southern Observatory and the International Astronomical Union. Now let's return to the story. Regular comets resemble dirty snowballs made of ice mixed with stones and dust in roughly equal proportions. When the sun heats the surface, the ice sublimates and carries away the dust, forming a tail. The core of Halley's Comet is about 15 kilometers long and 8 kilometers wide, with a density of around 600 kilograms per cubic meter. In contrast, the three Ibarra Atlas seem to have a completely different composition. Photometric analysis suggests a density closer to 400 kilograms per cubic meter, indicating that this is almost pure ice with minimal rock impurities. The low density explains early degassing. Pure yellow sublimates more effectively than dirty yellow, as there is no stone matrix isolating the interior. This raises new questions about where such a pure, icy substance could form and survive. Orbital mechanics maps its journey. Retreating from the current trajectory, astronomers calculate that it has been moving through interstellar space for at least 4 million years, considering its speed vector. Regarding local tranquility, the average movement of stars in our galactic neighborhood is 26.4 kilometers per second. This is typical for objects formed in different star systems and ejected due to gravitational interactions. The trajectory analysis becomes more specific. 3 Atlas bars approach our solar system from a region in space called the solar apex, roughly towards the constellation Hercules. This is the direction in which our solar system moves through the galaxy. Objects approaching from this side had maximum time to interact with the gravitational field of our sun, meaning they deviated the most from their original interstellar trajectories. Tracking its movement through space and considering the galactic rotation and star movements, indicating an origin in the thick disk of our galaxy, possibly 800 light-years away. This places his starting point somewhere in the star regions like Wolf 359 or Greenbridge 1830. These are not exotic places, but ordinary star areas where planetary systems form and occasionally break apart. Yet the chemical composition does not match the chronology. Spectroscopic analysis shows that the ice is not just water. It contains complex molecules that must have been broken down by cosmic rays during its multi-million-year journey. Carbon monoxide decomposes under radiation with an average half-life of about 1 million years in the interstellar medium. However, 3 and the Atlas bar actively degas carbon monoxide along with water vapor. The survival of these volatile substances suggests a much shorter travel time than indicated by orbital mechanics, or some form of protection during movement. One possibility is that the 3 and the Atlas spent most of their interstellar journey as part of a larger object, perhaps a fragment that recently broke off from a large comet. Fresh internal material, newly exposed to space, could preserve volatile substances that would have been removed from the ancient surface. Another explanation suggests the presence of protection. If Triton and Bara Atlas have a layered structure with frozen volatile substances buried beneath a protective layer of water ice and organic compounds, their inner layers may remain untouched for millions of years. Laboratory experiments show that even a few centimeters of ice can protect underlying materials from damage caused by cosmic rays. Size estimates add another detail to this puzzle. Judging by the brightness at various distances and the amount of material emitted, Tri and Bara Atlas have a diameter of about 2.5 kilometers. This is quite a significant size for an interstellar visitor, while Humo Amua is about 400 meters long. 2 and Baravolio had a diameter of about 1 kilometer. Most objects ejected from planetary systems are smaller, usually asteroid-sized pieces, ejected due to gravitational interactions with giant planets. The fact that something so large is ejected from its native system suggests a more violent origin story. Computer simulations of planetary system evolution show that the ejection of 1-kilometer-sized objects usually requires close encounters with gas giants or stellar companions. The energy required to accelerate an object 2 kilometers in diameter to escape velocity from a star system is colossal, equivalent to about 10 to the 15th joules, comparable to the kinetic energy of a large asteroid impact. One possibility is stellar evolution. As stars age and expand into red giants, they can disrupt the outer regions of their planetary systems. The red giant phase of a sun-like star can increase its radius to several astronomical units, heating and vaporizing comets that were previously in frozen orbits at great distances. Some comets completely evaporate, others heat up, change, and are sometimes ejected by the changing gravitational field as a star loses mass. This may explain the unusual sizes and composition of Tri and Bara Atlas. Perhaps this is a settler from a dying star system, partially processed in the red giant phase of its parent star and then ejected before its final destruction. Heating could alter its internal structure, creating a layered composition that allows for degassing. This outburst could retain volatile substances inside, removing them from the destructive stellar environment. Another scenario implies close stellar encounters. When two star systems pass a few light years apart, gravitational disturbances can eject objects from one system to another. Computer simulations show that this occurs regularly on galactic timescales, possibly once every 10 million years for a typical star system. Tri and Bara Atlas may be the result of such an encounter. Perhaps this is related to a binary star system, where tidal forces have destroyed the outer planetary material. The hypothesis of stellar collisions corresponds to the direction and speed of the approaching object Tri and Bara Atlas. Objects ejected as a result of stellar flybys typically retain speeds close to the local rest standard, consistent with observations of 26 kilometers per second. This moment also aligns with expectations. Starry encounters can suddenly eject objects, retaining flight capabilities that are lost in slower formation processes. Early activity also provides clues about how the object was formed. Objects condensing in the outer regions of young star systems, beyond what astronomers call the snowline, can include significant amounts of volatile substances. In our solar system, the snowline is located at a distance of 5 astronomical units from the Sun. Inside this limit, temperatures are too high for the condensation of water ice. Beyond it, water ice, carbon monoxide, ammonia ice, and other volatile substances can freeze on dust grains and grow, turning into planetesimals. If Tri and the Atlas bar formed beyond the snowline of their parent star, at a distance of 10 or 20 astronomical units, they could have captured the mixture of ices we observe today. The key point is the formation temperature. Carbon monoxide condenses at about 25 kelvins, water ice at 150 kelvins, and ammonia ice at about 80 kelvins. An object forming at different distances will capture various proportions of these materials. Temperature measurements confirm this model. Even at a distance of 16 astronomical units from our Sun, the surface temperature of Tri and Bara Atlas has risen by about 60 kelvins, which is enough to initiate the sublimation of the most volatile components. Carbon monoxide transitions to gas at around 60 kelvins under low pressure. Water ice requires higher temperatures, close to 150 kelvins. The fact that it releases both substances indicates a complex thermal environment within the object. Thermal modeling becomes specific. With a diameter of 2 kilometers and an albedo of about 0.04, similar to coal, Tri and Bara Atlas absorb most of the sunlight that falls on them. At a distance of 7 astronomical units, this results in about 1 watt per square meter of heating. This may seem insignificant, but it's enough to trigger sublimation in the first meters of the porous icy structure. The conduction of heat through the inner layers depends on the porosity and composition. If the Atlas comet has a typical porous structure with 70% void, heat penetrates slowly, leaving the interior cold while the surface warms up. This creates a temperature gradient that can facilitate the sublimation of various materials at different depths. Carbon monoxide sublimates near the surface, while water sublimates at greater depths, forming a complex mixture of gases observed by astronomers. The production of dust tells a different story. Unlike typical comets that create spectacular tails visible to amateur telescopes, the object Tri and Bara Atlas produces relatively little dust compared to gas. The ratio of gas to dust is about 10 to 1 by mass, significantly higher than the standard 3 to 1 ratio for comets in the solar system, suggesting that the ice is relatively pure and not mixed with large amounts of rocky material. Pure ice sublimates more efficiently and produces less visible dust. This is another hint indicating the formation in the outer regions of a planetary system, where rocky material would be scarce in parts of the outer disks of protoplanetary systems beyond the snowline. The density of dust is lower there, and ice dominates over solid material. Objects forming in such conditions would naturally have a high proportion of ice to rock. Tracking its trajectory through our solar system reveals more about its origin. Tri and Bara Atlas came from the galactic coordinates direction, L equal to 275 degrees, B equal to minus 15 degrees. In simpler terms, this direction points to the constellation Leo. It moves almost perpendicular to the plane in which most planets rotate. This trajectory aligns with an object that entered our solar system from the general direction of the galactic disk, where star encounters occur more frequently. Orbital integration shows that the closest approach to Earth occurred on May 14th. 2024, at a distance of 1 whole and 1/10 astronomical units, about 160 million kilometers. This is a safe distance, but close enough for detailed spectroscopic observations. The Hubble Space Telescope captured images showing a compact nucleus with a faint coma extending about 10,000 kilometers, typical for an active comet. However, spectral analysis revealed something unexpected. The water vapor was not just ordinary water. Isotopic measurements showed a deuterium to hydrogen ratio of about 300 parts per million, roughly double that found in Earth's oceans and 3 times higher than in typical comets of the solar system. This isotopic signature indicates formation in an environment very different from anything in our stellar neighborhood. Deuterium is formed in specific nuclear processes, mainly during nuclear fusion at the stage of the Big Bang and in the cores of certain types of stars. The ratio of deuterium to hydrogen in various materials reflects the conditions under which they formed. Earth's oceans, with a deuterium ratio of about 150 parts per million, likely received their water from asteroids and comets formed in a distant corner of the solar system. The high deuterium content in 3 objects known as Kiba-Ratlas indicates their formation around a star with different metallicity than our Sun, occurring in an area where temperature and pressure during the early stages of planetary system formation differed from those here. Theoretical models predict higher ratios of deuterium in systems formed from interstellar clouds, enriched by previous generations of stellar nucleosynthesis. This discovery highlights how much we learn about interstellar objects until 2017, when Oumuamua became the first confirmed interstellar visitor. Most astronomers considered such objects rare curiosities, expecting perhaps one to be detected each year passing through the inner solar system.